Okay, hi everyone, welcome back to this video series on data centers. I want to have a look here at figure 4.3, and this is the DHCP client 4-step process. So we have client DHCP discover, server unicast DHCP offer, client broadcast DHCP request, server unicast DHCP ACK. So the following is the 4-step process a client takes to receive an IP address from a DHCP server. The DHCP client broadcasts a DHCP discover message looking for a DHCP server port 69. The DHCP server that received the DHCP discover message sends a unicast DHCP offer message back to the host. The client then broadcasts to the server a DHCP request message asking for the offered IP address and possibly other information. The server finalizes the exchange with a unicast DHCP acknowledgement message. DHCP conflicts. A DHCP address conflict occurs when two hosts use the same IP address. This sounds bad, doesn't it? Well, of course it does. During IP address assignment, a DHCP server checks for conflicts using the ping program to test the availability of the address before it is assigned from the pool. If no host replies, then the DHCP server assumes that the IP address is not already allocated. This helps the server know that it is providing a good address, but what about the host? To provide extra protection against the also terrible IP conflict issue, the host can broadcast for its own address. A host uses something called gratuitous ARP to help avoid a possible duplicate address. The DHCP client sends an ARP broadcast out on the local LAN or VLAN using its newly assigned address to solve conflicts before they occur. So if an IP address conflict is detected, the address is removed from the DHCP pool scope, and it is also important to remember that the address will not be assigned to a host until the administrator resolves the conflict by hand. Automatic private IP addressing, APIPA. What happens if you have a few hosts connected together with a switch or hub and you don't have a DHCP server? You can add an IP address by hand. This is called static IP addressing, but Windows provides what is called automatic private IP addressing, APIPA, a feature of later Windows operating systems. With APIPA, clients can automatically self-configure an IP address and subnet mask basic IP information that hosts use to communicate. When a DHCP server isn't available, the IP address range for APIPA is 169.254.01 through 169.254.255.254. The client also configures itself with a Class B subnet mask of 255.255.0.0. However, when you're in a corporate network working and you have a DHCP server and your host knows that is running this IP address range, this means that either your DHCP client on the host is not working or the server is down and can't be reached because of a network issue. I don't know anyone who's seen a host in this range and has been happy about it. The host-to-host layer protocols. The main purpose of the host-to-host layer protocol is to shield the upper layer applications from the complexities of the network. This layer says to the upper layer, just give me your data stream with any instructions and I'll begin the process of getting your information ready to send. The following sections describe the two protocols at this layer: Transmission Control Protocol TCP, User Datagram Protocol UDP. Transmission Control Protocol TCP. Transmission Control Protocol takes large blocks of information from an application and breaks them into segments. It numbers and sequences each segment so that the destination's TCP stack can put the segments back in the order and the application intended. After these segments are sent, TCP on the transmitting host waits for an acknowledgement of the receiving end's TCP virtual circuit session, retransmitting those aren't acknowledged before a transmitting host starts to send segments down the model. The sender's TCP stack contacts the destination's TCP stack and to establish a connection. What is created is known as a virtual circuit. This type of communication is called connection orientated. During the initial handshake, the two TCP layers also agree on the amount of information that's going to be sent before the recipient's TCP sends back an acknowledgement. With everything agreed upon in advance, the path is paved for reliable communication to take place. TCP is a full, complex, connection-oriented, reliable and accurate protocol, but establishing all these terms and conditions in addition to error checking is no small task. TCP is very complicated and, not surprisingly, costly in terms of network overhead, and since today's networks are much more reliable than those of yore, this added reliability is often unnecessary. Most programmers use TCP because it removes a lot of programming work. However, real-time video and VoIP use UDP because they can't afford the overhead. TCP segment format. Since the upper layers just send a data stream to the protocols in the transport layer, I'll demonstrate how TCP segments a data stream and prepares it for the internet layer. When the internet layer receives the data stream, it routes the segment as packets through an internetwork. The segments are handed to the receiving host host-to-host layer protocol, which rebuilds the data stream to hand to the upper layer applications or protocols. Figure 4.4 shows the TCP segment format. The figure shows the different fields within the TCP header: 16-bit source port, 16-bit destination port, 32-bit sequence number, 32-bit acknowledgement number, 4-bit header length, reserved flag, 16-bit window size, 16-bit TCP checksum, 16-bit urgent pointer, options, data. The TCP header is 20 bytes long or up to 24 bytes with options. You need to understand what each field in the TCP segment is. Source port, the port number of the application on the host sending the data. Destination port, the port number of the application requested on the destination host. Sequence number, a number used by TCP that pulls the data back in the correct order or retransmits missing or damaged data, a process called sequencing. Acknowledgement number, the TCP octet that is expected next. Header length, the number of 32-bit words in the TCP header. This indicates where the data begins. The TCP header, even one including options, is an integral number of 32 bits in length, reserved, always set to 0. Code bit flags, control functions used to set up and terminate a session. Window, the window size the sender is willing to accept in octets. Checksum, the cyclical redundancy check, CRC, because TCP doesn't trust the lower layers and checks everything. The CRC checks the header and data fields. Urgent, a valid field only if the urgent pointer in the code bits is set. If so, this value indicates the offsets from the current sequence number in octets where the segment of non-urgent data begins. Options, maybe 0 or a multiple of 32 bits, if any. What this means is that no options have to be present. Option size of 0. However, if any options are used that do not cause the option field to total a multiple of 32 bits, padding of zeros must be used to make sure the data begins on a 32-bit boundary data handed down to the TCP protocol at the transport layer, which includes upper layer headers data handed down to the TCP protocol at the transport layer, which includes the upper layer headers. Let's take a look at a TCP segment copied from a network analyzer. TCP control protocol, source port 5973, destination port 23, sequence number 14563899907, ACK number 124056456, offset 0, reserved %0000000, code %011000, ACK is valid, push request Windows 61320, checksum 0x61A6, urgent pointer 0, no TCP options. TCP data area VL 5 plus 5 plus 5 plus 5 7 6 4C 1935112 B 1935112 B 193511, frame check sequence 0x0D00000F. Did you notice that everything I talked about earlier in the segment, as you can see from the number of fields in the header, TCP creates a lot of overhead. Application developers may opt for efficiency over reliability to save overhead, so user datagram protocol was also defined at the transport layer as an alternative. User datagram protocol UDP. If you were to compare user datagram protocol UDP with TCP, the former is basically the scaled down economy model that's sometimes referred to as a thin protocol, like a thin person on a park bench. A thin protocol doesn't take up a lot of room, or in this case more bandwidth on the network. UDP doesn't offer all the bells and whistles of TCP either, but it does do a fabulous job of transporting information that doesn't require a reliable delivery, and it does using far fewer network resources. UDP is covered thoroughly in requests for comments 768. There are some situations in which it would definitely be wise for developers to opt for UDP rather than TCP. One circumstance is when reliability is already handled at the process application layer, network file system NFS, and handles its own reliability issues, making the use of TCP both impractical and redundant. But ultimately, it's up to the application developer to decide whether to use UDP or TCP, not the user who wants to transfer data faster. UDP does not sequence the segments and does not care in which order the segments arrive at the destination, but after that, UDP sends the segments off and forgets about them. It doesn't follow through, checks up on them, or even allow for acknowledgement of the safe arrival, complete abandonment. Because of this, it's referred to as an unreliable protocol. This doesn't mean that UDP is ineffective, only that it doesn't handle issues of reliability further. UDP doesn't create a virtual circuit, nor does it contact the destination before delivering information to it. Because of this, it's also considered a connectionless protocol, since UDP assumes that the application will use its own reliability method. It doesn't use any. This gives an application developer a choice when running the Internet Protocol stack: TCP for reliability or UDP for faster transfer. So it's important to remember how it works, because if the segments arrive out of order, very common in IP networks, they'll just be passed up to the next OSI DoD layer in whatever order they're received, possibly resulting in some seriously garbled data. On the other hand, TCP sequences the segments so they get put back together in exactly the right order, something UDP can't just do. UDP segment formats. Figure 4.5 clearly illustrates the UDP's remarkably low overhead, and compared to TCP's hungry usage. Look at the figure carefully. You can see that UDP doesn't use windowing or provide for acknowledgements in the UDP header. So here we have source port 16, destination port 16, length 16, checksum 16, data if any. It's important for you to understand what each field in the UDP segment is: source port, port number of the application on the host sending the data, destination port, port number of the application requested on the destination host, length of UDP header and UDP data, checksum of both the UDP header and UDP data fields, data, upper layer data. UDP, unlike TCP, doesn't trust the lower layers and runs its own CRC. The following shows a UDP segment caught on a network analyzer. UDP user datagram protocol, source port 1085, destination port 5136, length 41, checksum 0x7A3C, UDP data area Z001589600000011000000 C2C C2E03Z4302 0A000A0080430080. Frame check sequence 0x00000000. Notice that low overhead. Try find the sequence number, AC key number and window size in the UDP segment. You can't, because they just aren't there. Key concepts of host-to-host protocols. Since you've seen both a connection-orientated TCP and connectionless UDP protocol in action, it will be good to summarize the two here. Table 4.1 highlights some of the key concepts that you should keep in mind regarding these two protocols. You should memorize this table. TCP, sequenced, reliable, connection-orientated, virtual circuit, acknowledgements, windowing, flow control. UDP, unsequenced, unreliable, connectionless, low overhead, no acknowledgement, no windowing or flow control of any type. A telephony analogy could really help you understand how TCP works. Most of us know that before you speak to someone on a phone, you must first establish a connection with them wherever they are. This is like a virtual circuit with the TCP protocol. If you are giving someone important information during a conversation, you might say, you know, or ask, did you get that? Saying like this is a lot like a TCP acknowledgement. It's designed to get you verification from time to time, especially on cell phones. People also ask, are you still there? They end their conversations with a goodbye of some kind, putting closure on the phone call. TCP also performs these type of functions. Alternatively, using UDP is like sending a postcard. To do that, you don't need to contact the other party. You simply write your message, address the postcard and mail it. This is an analogous to UDP's connectionless orientation. Since the message on the postcard is probably not a matter of life and death, you don't need an acknowledgement of its receipt. Similarly, UDP does not involve acknowledgements. Let's take a look at one figure, one that includes TCP, UDP and applications associated with each protocol. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.